and welcome to the seminar about raw material and production cost optimization for the steel industry by Cassotis. I am Emmanuel Marchal, founder and partner at Cassotis. I've been serving steelmakers for almost 15 years now, and with such kind of solution that will be presented during this seminar. This seminar will be split into three main parts. The first one will be a global presentation of the solution that will then be demonstrated. And finally, we will have time to answer your questions at the end of the seminar. So please, any questions you may have, write it in the chat. Any single question will be answered at the end of the seminar. This is not the only web event that Cassotis is doing. So please follow us on LinkedIn. We are releasing many content every week that for sure will be your interest. And last thing before starting, this seminar will be recorded and available on YouTube right after. In case someone couldn't join us and would be on his or her interest, feel free to share the link to the video. Thank you for your support. So let's start with the presentation about this unique solution in advanced analytics and mathematical optimization to optimize all the strategic and tactical decisions of a steel plant. And this is valid for the budgeting exercise, meaning the annual budget or even the monthly revision that are revised every month in terms of raw material purchase, production level, being final product, or even the intermediate product in your ore production chain. And talking about intermediate products, we also have to set the specifications of it. Not those ones that are supposed to be valid for years, but a kind of dynamic specifications which actually highly depends on the other decisions that I mentioned before, purchase of material, production level, and that should be revised together with those when those decisions are being re-optimized. We are talking here about chemical composition, physical quality of all those intermediate products. Procurement decisions, where you are asked to evaluate new suppliers of raw material, or even to determine what is the value in use of those types of materials. And finally, sales decisions, being the portfolio order book optimization, which is based, among other things, on the product rentability analysis. And how does that work? Well, with a mathematical model made by balances, mass, chemical, thermal, or even the energetic balance of the whole production plants, but also predictive model made by empirical equations to predict the physical quality of a product, or even estimate how this quality is actually impacting the subsequent processes in terms of yields, fuel consumption, pace, production pace. And finally, from the model part, we also have obviously the cost and all the revenues that are related to those decisions in terms of cost and revenues, including the byproducts. This model is fed by input parameters from raw materials, from the process, and from the market. This is when the market is part of the scope of the model, when you want the model to optimize the sales part. Which kind of product should I produce in which quantity? Obviously, the system is restricted by some constraints. The final specification of the steel is one of them, but we also have to account for operational limits, logistic capacities, or even environmental constraints. You may be limited in the consumption of a cheap material by your emissions of CO2, SO2, dust. All those considerations are being contemplated in the model. And finally, to have the full package of what we call a mathematical problem, we need to set a mathematical objective, which is in this case a profit maximization when the market is inside the scope, or if we decided to fix totally this production, the problem turns into a cost minimization. And this, after applying many techniques, algorithms of optimization, the system will deliver insights for you to make great decisions in terms of raw materials, process, product, and market. And what are the benefits of such a model? Obviously, a huge cost reduction or profit increase is expected by the fact that you are optimizing your whole production chain in a unique model, where the decisions that involves different departments are optimized together. For instance, the quality-related decisions used to be the result of a compromise between people agreeing on a value, on a midterm quality that not necessarily is the best one to choose to achieve the best objective globally. Also, this solution would be a unique tool used by different people from different departments, from procurement, operations, and sales. And in this tool, we will aggregate all the knowledge from the experts themselves, or even from the data. And this knowledge base will grow with time. You will not lose the knowledge when people are retiring or even leaving the company. All this knowledge will be incorporated in the model. And such a solution can actually be seen as a strategic digital twin of your plans, because you will be able to simulate and actually optimize any new situation even after unexpected event. We may think about the blockage of the Suez Canal, for instance, where steelmakers have to readapt the whole planning of production according to dealing with a delay in the raw material procurement, for instance. The model is a great tool to be able to react and to reduce the negative impact of such an unexpected event. And this model will probably replace local models that people may already using, most probably in Excel, but everything in an integrated way. By the fact that we are talking here about the optimization of decisions at the strategic and tactical level, where decisions worth millions of dollars, any optimization, any utilization of the model will bring huge value or huge savings that turns consequently in the fastest payback of this system in the whole software industry. The savings will obviously depend on your process. That's why we have listed in those two slides some example of decisions that have been simulated together with our customers, together with the main considerations that are somehow impacted by the decisions. I say the major ones because actually any decisions may impact all the decisions of the whole plant. But we have listed here the major ones. Together then with an estimate in terms of dollar per ton of steel, so that you can estimate by how much you should expect savings by optimizing and using this system. For instance, in the blast furnace route, the decisions that we have listed involves the coal blend, all the metallic charge at the sinter, at the blast furnace, at the converter, as well as the ferroalloys that can be where we can have some savings by the fact of using iron ore with a higher concentration in manganese, for instance. And this is valid for the blast furnace route, also for direct reduction route, where the main decisions will be more about the metallic charge of the direct reduction plant itself and the reforming of the gas, as well as the metallic charge of the electrical arc furnace. For the stainless steel, we even have more flexibility in the usage of the scraps at the furnaces, because we can use carbon or stainless scraps based on their price, on where they will be added, considering the limitation of a buildup in the process. Many users already optimize the decisions in different plants. We have here two testimonials. One is from CSN, the other one is from Gerdau. And we have on the right the full list of the steel makers using our system today. At Ternium, we implemented the solution at Ternium Argentina and Mexico. And Gerdau, it's about their integrated steel plants at Ouro Branco, as well as the semi-integrated steel plants with the charcoal blast furnaces in the state of Minas Gerais in Brazil. Well, for this seminar, I decided to describe further 4 main usage of the tool. The first one being about these intermediate product specifications. We have simulated with the model here, it's an integrated steel plant, a carbon steel plant, where we have plotted then the cost of coke and the cost of hot metal, production cost, for many coal blends, different coal blends, that has been sorted from left to right according to the hot metal production cost. And even if we observe a trend that show that by reducing the cost of the coke, you are somehow reducing the cost of hot metal, we can see that the cheapest hot metal is not necessarily made by the cheapest coke. And this is valid for any intermediate product. We may think about sinter with hot metal, sponge iron with steel, hot metal with steel, or even inside the steel making shop. Another case that I've mentioned even in the introduction is about the marginal value, which is a concept very similar to the value in use, but applied to the optimization world. Indeed, the optimization will show you the list and the optimal blend of material to be used to achieve your objective. In this mix, some material from some supplier will not be being used by the system. They will appear in green in this table. And this means that the price of the material do not compensate the quality of it. But it then means that it does exist a price lower than the one which is offered, where the model will start using it. The material will start being attractive for the system. And this is exactly the interpretation of the marginal value that we can see here in the graph, or even in the attractiveness, which is simply the difference between the marginal value and the price. And we can see that for all the material with a negative attractiveness, indeed, the material has not been consumed. But we can see here also material with a positive attractiveness, which means that those materials has been used at maximum capacity. And this information of the marginal value will tell you at the maximum price that material will remain being used at maximum. Or even differently, the value of the attractiveness is the savings that you are having by using 1 ton of this material. A next case that I wanted to show you is about the marginal cost and the marginal revenue, which are two major and the most important concepts in the microeconomics to determine the best production level, which is represented in the y-axis here, to achieve the highest profits. So we have here two curves, marginal cost in blue, and here is the marginal revenue. For different level of production, what we observe is that marginal cost tends to increase with production because you are using more expensive material to achieve a higher production level. The cheapest one, or the one with the best ratio between the quality and the price, as being used for the first tons that you decide to produce. Also, by pushing up your machine to a higher pace, you somehow required a higher quality in your material and product to achieve such a production pace. On the other hand, on the marginal revenues, we are first attending customers asking for a product with a higher contribution margin, with a higher marginal profit, which is actually exactly what is represented here. The space between, the difference between those two curves represents the marginal profit that we have, and then by all the factors that I just mentioned, tends to decrease with the higher production. At a point of having those two curves intersect. And this intersection will determine the best production level to operate your plant that will guarantee the highest profits. And this is not necessarily the maximum capacity of your plant or even the maximum demand. An interesting result together with those two curves are the mix of product, because in this case, the order book was also optimized. That's why those two curves have this behavior. And here, in this chart, we can see how the order book will then evolve according to the production level. And obviously, first, we have an increase in the production of the product with the higher marginal profit contribution in the overall profits. But then, at a certain point, we may reach what we call the portfolio effect, which is due to some bottlenecks in your production. Indeed, if you're in some production units, you have some competition in terms of capacity for different products. When you reach the maximum capacity with the highest margin products, if you want to increase more and more the production, you are somehow obliged to remove from your order book some steel grades. This is the case for the steel number 6 and steel number 8 that are after a certain point reducing to be able to produce more by producing products that requires or that have a higher production pace on that bottleneck. Well, all those results that I've presented here are produced by the mathematical model that I've explained, but also extracted from a graphical interface, which is called Quandec, that are used to host this mathematical model. And this interface has been developed in a way to be very user-friendly for the end users to make their decisions and analysis. We have here a list of features that brings a lot of value in each utilization of the system, being comparing scenario, importing data to evolve the model with new correlation, with new, more recent data, importing data from external source, and so many features that will be actually showcased in a demo. And for that, I will ask Fabio to conduct this demo for you. After that, I will come back to answer your question. Fabio, the floor is yours.
Thank you, Emmanuel. Hello, everyone. My name is Fabio. I'm a senior manager at Cassotis, and I'm going to present some of the features of our solution. Let me just change the perspective here so it gets easier for you to see. There we go. So the first thing that we can see once we access the application is this main menu. On the left, we see that we are here on the masters and scenarios. I'm going to explain later what it is. When we go to the analysis, we see results of previous analysis that we've made. And by that, we're talking about marginal cost, marginal value of a specific raw material, a sensitivity analysis that we made over a parameter or over a variable on the model. We also have the data warehouse, and here what we have is all the historical data that was inputted into the application, and also the regressions that were created. I'm going to explain more in detail later this part. But when we go back to masters and scenarios, we see a list of data sets. These data sets are masters, which are the references. A nice example would be a budget reference, so an optimized budget. And from that master, we can create multiple scenarios. For instance, I have my scenario here that I'm going to access. It has no changes in the journal, but it was already there. And on the left, we can see that the model, it is structured in a way that is easy to navigate. So we try to divide it by department. If we look at the main input data that is necessary to run an optimization, we would go to the raw material. We have a list of all the raw materials. I'm gonna take a more detailed look at the iron bearing materials here. So here we have the list of fine ores, lumpors, and pellet suppliers. And for each supplier, we would have a price, availability, physical or chemical composition and physical properties if we are talking about something that is relevant to this optimization as well. And we're going to have this for every raw material that we consider in the optimization. One other part that is very important for the optimization is the other part, so the demand. When we look at the demand, here I'll go to the slabs and I go to the input materials again, and I can see all the demand that is being set for this optimization. I have the amounts, the maximum and the minimum demand, and the prices for each steel grade in each market. One other thing is that this steel should follow some specifications, some chemical specification. When I go to the secondary refining, I can see the input that represents the minimum and maximum value for each chemical compound in this steel. And the idea is that the model will optimize the integrated products in a way that, of course, it's gonna respect the final specification and then the other intermediate specification as well if there is in this data set. Once we have defined all the inputs, of course, these are not all the inputs that it has. I'm just showing a few. I can optimize. Since I didn't make any changes, these optimizations runs very fast. When I go, we can see detailed results for each department. I can see how the model is optimizing the blend at the sinter plants. At the sinter plant, we see it divided by iron-bearing material, fluxes, fuels. I can even interact with the charts and see how it is split here. I can interact with the tables as well. I have more detailed information on this blend down below. If we go to the blast furnace, I could see the proposal, the amount of hot metal that is being proposed to be produced, its quality as well. We could see some operational variables being optimized as well. In the casters, we can see the amount, the total slab produced at the casters, the operating rate, which was 89. This operating rate is respecting the fact that it has a maintenance rate of 2.2, and the optimized result it still has an idle rate of 7.84. So there was still availability in this process to produce, but somehow the model found that it was good to stop there. It was optimal there. There could also be other results, like, for instance, we can look the pollutants results here, and we can see the CO2 emission divided by department, how it increases at each department, and maybe it decreases on the generating credit because of the in this case for the amount of electricity that is being sold. So even though the model is generating, it's not being counted on the amount of CO2 considered in the ton of slab. So we can see other pollutants as well, and there it goes. But one thing that is very important when we're talking about optimization is how the optimization relates to your actual operation. And one thing that we have is a list of indicators, which are variables that we select to follow and relate to the historical data. And here we can see that on this optimized results, all these variables that are green here, we have results that are okay inside the average, very close to the average actually. Let's say this one, it's 19 and the average is 19.13. But we also have some variables that start going further from green, meaning that is going closer to its limit. We could also have a red variable here that had a value that was on the optimal solution. It is a value that was never seen before, maybe because a bound was not set, something was not right, and the application would easily show that we're talking about an optimization that is out of range. But of course, it's only a matter of updating the bounds and getting the proper results. In the hot metal, we have something interesting here. Let's see more specifically to the sinter content of the hot metal, because as Emmanuel mentioned before, our model is a combination of theoretical and empirical equations. The sinter content is an example of one of the empirical equations that we have in the model. When I go to equations, I see the list of all evolving equations that we have in the model. I'm going to maximize this visualization here. And we can see here this equation, which is the one responsible for the silicon content of the hot metal. It came from a regression with an R-square of 53%, and it actually predicted by 3 variables. Here we see the average value of the silicon content, the 3 predictors, which are the hot metal, the productivity, and the coke rate, its coefficient, and the pivot, or the average value for each one of the predictors. This equation, I can analyze the impact. So I have one that was 0.38. That is, it is a little, it's not exactly the average value that we have coming from historical data. And we can see why we actually have this result. It is coming from the impact of each predictor, and its value is ordered here. And we can see the productivity with the highest impact has an impact of minus on the reduction of 0.02. So the pivot was 2.26 with a value of 2.36, an increase, and a negative coefficient. We have a decrease of this value, and this goes for every equations that we have here listed. We can make this analysis for every one of them. These equations, they can evolve. So I can replace this equation with another one. If I'm not happy with this one, I can come here. I can replace it by another theoretical equation, which I will introduce the way that I want, defining the predictors that I want, the coefficients and their goals. But it could also come from a regression. Regressions are defined in the data warehouse. When we go to the data warehouse, as I mentioned before, we have all the historical data that was inputted into the application, but we also have the regressions. Here, as an example, I have the Coke CSR index that came from a regression produced from the historical data. So we have the CSR being predicted by all these predictors here. I can make some configurations on how I want the application to look for these regressions, to define these regressions. And I can take a look at the historical data that would be used on the creation of the regression. And once everything is set, I can see all the proposed regressions. These proposed regressions are the combinations of all the predictors, and it makes all the combinations, and it relates to, it evaluates its adjusted R-square, and they are ordered by this right here. So you can see, if I go down, I can see all the possibilities, all the possibilities of combinations of these predictors. I can even take a look at a more detailed statistical data, looking here at the scatter of this equation. Here we're talking about a quite good regression here with this scatter. So once I have these equations here, I can favorite the ones that I prefer. When I go back to a scenario, I can change this equation. I could come here, I could replace by regression and select one of the ones that I have to change this equation. But here I'm not gonna make it. The main thing of the application is to change, create scenarios, and make new hypotheses. Let's suppose that we, for some reason, one of my supplier is not able to deliver the amount of coal that that is said that we would. I could change this data via an Excel table, via a CSV table via a web service that will be implemented to directly update the data. But here I'm going to make a simpler example with an actual change in one of my tables. So supplier E is being consumed here. That's the amount consumed, that's the availability, 300 and 188. What I'm going to do is reduce this availability to 0. Once I reduce this availability, I go back to the journal and the value is changed. So it changed to 0, I can see in the journal. I'm gonna optimize to see what actually happens. I could navigate here and see every result, but there is an easier way to make a comparison. I'll go back here. I'm gonna select my scenario. I'm gonna hit compare, say that I wanna compare it to the budget. And I can see here from this perspective, an easier way, all the variables on a comparison perspective. So here, I'm looking in detail how it changed. If I go to the plant, the global economics, I can also see, and every variable on the model would be listed here. I can even create a report. Let's say that there are some variables that I want to look more in detail, and I want to save this for later. What I would do is I would drag. Let's drag this one here on a specific variable, coal plant, COG. So how it impacted the code. And with this, I have a specific report showing a detailed variation on the data sets that I have. There are actually many other features in Quandec. With the time that we have, I believe that this is everything that I can show you now. Quandec is a collaborative tool, so it's supposed to be used by many users at the same time in a collaborative way. There are other analysis, more advanced analysis that could also be made. There are many things to talk about. I thank you for your time, and now I'll pass it back to Emmanuel so he can answer any questions that you might have.
Thank you, Fabio, for this great demo. So let's come back to the presentation. Just before the question and answer part, for those who didn't know Cassotis, this solution that we are presenting here is not the only solution that we are implementing for the steel industry. Actually, we are a consulting firm building, developing mathematical models for any decision making. And we have here a list of example of typical decisions that can be optimized in the same way we showed you this optimization model for the process of the steelmaking. So this will then end this presentation and demo part. You have here all the contact info if you want to enter in contact with us. And I will then now start with by looking at the questions that you may have asked in the chat. So, okay, I can see already a few questions. Thank you for that, and thank you for your participation. The third question is about production units. Is every production unit represented in the model? Indeed, in the demo, we saw only one sinter plant, one blast furnace, but the model is obviously prepared to model every productive unit as it is, so as a real entity with its own blends, process variable that can be optimized in case two facilities are sharing some blend of material. This is a constraint that we will add to the model. in the customization phase of the project, where we will implement that model for a specific plant. Okay, so I think I answered the question. If it is not, please continue asking your question in the chat. Will the tool incorporate induction furnaces as a source of hot metal in the stainless production? Actually, it could be. We did not describe that much all the type of processes, mainly in the steel shop, where we can indeed have different type of furnaces. I think I mentioned electrical arc furnace in the presentation, but obviously an induction furnace could be also implemented and modeled and integrated with the rest of the process, and optimize its blends, the energy consumption, which will be slightly different in comparison with an electrical arc furnace. And actually, we already did projects with iron foundries, where we already have models for induction furnaces. Another question. Will the tool optimize over plants located over two separate locations within the same group? Okay, yes, indeed, that's happened, that you have a network of plants where actually you have decisions to optimize at each plant, but you might have corporate decisions. Typically, they are about procurement. You may have contract with suppliers which are valid for the two plants, and actually the decisions to sign a contract with a supplier is about the two plants and not only one, or even the markets. You can have, it is usually the case, a unique market that can be attended by two or many different plants. And the answer is yes. We will obviously increase the complexity of the model, but the model is ready for that, to have different productive plants, different locations in the same model, to be able to optimize all those corporate decisions. Next question, is this tool clouds-based? Actually, yes. We have different ways of deploying this system. Most of the customers are using the tool hosted in our cloud, but it's also possible to install all the systems and all the software part on premises. So it's quite flexible, actually, on that part. Okay, next question. So many questions. Thank you for that. Thank you for your participation. How this solution implemented? And is it possible to develop a project remotely? Okay, thank you for that question. So this solution is implemented in a project where we will start by collecting all the information required to actually customize the model that we already have. The demo that you have seen is somehow our basic version of the model with simple relations between all the variables, but obviously the project will be required in order to calibrate all the equations, or even change some equations, because with the expertise and knowledge that your expert have, we may change the way we are modeling the way of estimating the fuel consumption at the blast furnace. We have a model that we can calibrate, or we can totally replaced by, I was mentioning local models used in Excel. It's sometimes happen that we replicate the equation that were being used in the local model, and we incorporated it in our model such that we use exactly the model that was used for years in the group, but now integrated with the rest of the plant. And can this project be conducted remotely? Yes, obviously. I think everybody has to adapt to this new reality now since more than 1 year, and we have actually. It was already the case before. Most of the work was done remotely. All the modeling part, the calibration, the customization also of the interface, what you have seen, like the tables and the charts, everything can be adapted to your requirements. And most of this job is actually done remotely. And for the meetings that we need to have with your experts to exchanging about the process and the model, I think now we are actually ready to conduct all those meetings remotely. And who knows when things come back to a normal reality, we may obviously conduct part of this model also in making visits to your plants. Okay, let's see other question. What if during optimization an optimal result is not achieved? Will the tool show me what all areas are not optimized, and is there any way to troubleshoot the unoptimized areas? Okay, interesting question indeed. As we are talking here about an optimization model, which is restricted by constraints and using many data, we never know that we have set limits that are just impossible to fulfill at the same time, because maybe we made a mistake or we forget to remove a bound on a variable, which makes that an equation is totally outside its feasibility range, or for any reason we introduced a mistake in the data. The model will then clearly show you that it was not possible to optimize in those conditions, and will shortlist the variable or the constraints that it was not possible or to calculate or to fulfill, such that you can easily analyze what would be the possible cause of it. And another way to in combination to that list of infeasibilities, we know that the problem has been introduced by looking at the journal. You have seen that every change that we make to the data, to the equations, to the bounds, are listed in that journal. So by looking at the journal, by looking at infeasibilities, it's quite easy to understand really what was causing the infeasibility. Quite technical question, I like it. Next question: is there a limit in number of grades of final product or final products that the tool can handle? The answer is yes. There is a limit for the optimization, but usually we are able to introduce all the data per grade, and we make just an assumption according to the order book of the year or the months, to group those steel grades in families, in groups, and then we can deal with hundreds of grades or of products. And actually, some of the analysis, for instance, the marginal cost per grade, which has not been showcased in the demo, and I didn't mention it even in the presentation, but there is a lot of kind of advanced analysis that we can do on top of the model. One is the estimate of the marginal cost per steel grades. And there we are able to present the result exactly on all the individual grades. So usually we introduce all the information. For the optimization itself, it would be maybe too much variable for the model to handle. So we are making groups just for the optimization part. But even with that limitation, we are able to calculate interesting insight for each steel grades, for the rentability analysis I was mentioning in my presentation, for instance. Are you ready to consider carbon credits or carbon emission penalties in the model? Yes, and we know that this is a subject that are more and more required by the fact that today we have much more restriction on that, depending on where the plant is located. Indeed, if you are in Europe, the emission can be actually related to a cost, to a price for the credits. Otherwise, we can also limit the emissions. And as I think we saw it in the demo, Fabio presented the CO2 emission, but we have many of pollutants that we are able to predict. CO2, SO2, NOx, dusts. Some are pure balances, which do not require any empirical equations. Others are estimated by regressions. There are many process variables, and obviously raw material properties that makes that to have more or less pollutants emissions. And so yes, the question, the short answer now is yes, it is possible to account both for credits that will be incorporated in the objective, in the economical objective, or as a limitation. And then you will be restricted in your choice of material or setup of the machine to a certain limit in terms of concentration, global mass of emission, depending on the type of restriction. Will the tool incorporate two different plants having different production grades and different chemistry? Will the tool incorporate two different plants? Well, integrate two different plants could make sense if we have indeed decisions that are being made and that involve the two plants. If there is a clear split between those two plants and they are not sharing any material, any market, anything, I think that we will get much better result by having two separate models, and each of them will be optimized separately, than creating a big model where we actually have two sub-models in it. I'm not sure the algorithm for the optimization will like the fact having to actually solve two problems, because then we will increase the consumption in memory and may require more computing time for no benefits at the end for the decision itself, unless there are a few decisions that make sense to integrate the two. So the answer would be it depends, actually. Okay, I think I'm so happy to have so many questions to answer. I hope we will have time to answer all of them. Okay, next questions. Supposing that we do not have a system with historical data so evolved, is it relevant to implement your solution? Okay, this is indeed one of a concern that people have, then I'm not sure I'm already ready for that solution because I don't have that much data and so on. The final model that will be finally released at the end of the project is a balance between theoretical models and empirical equations. Obviously, empirical equations require data, but they're always an alternative to an empirical equation by using an equation that we know will have a good behavior and represents very well the concept that is being discussed. And we may then use coefficients, typical coefficient that we encounter in the literature, or we can keep the average value coefficient that we have in our demo, which is more or less an average of the coefficient that we had in our different projects in the past. So there is always solution, even and relevance for a plant to implement such a model, even they don't have that much data to calibrate the model. We will then have more assumptions behind the decision. Obviously, yes, but this is not that problematic because the benefits of the model do not come exactly from the fine calibration of the model, but yes, of the integration of simple mass and chemical balance where there is not that much empirical relations. Already that will bring many benefits just by integrating all those decisions in a unique model. And the data and the fine tuning will obviously improve the decision that you are making, but I would say that you will already have huge savings even without that much data. Okay, I see two more questions. What are the teams that must be involved in such a project? Many of them, because we need knowledge and expertise in many aspects that are contemplated in the model. So obviously, people from the production, people from the procurement, from the sales, again, if this is in the scope of the model, the planning, because this tool is definitely used to make the monthly revision of the budget, which is usually under responsibility of the planning team. So there will be end users, even they don't have many input data to deliver for the model. They will be key users in the utilization of the tool. And well, IT people for a few maybe interfaces with other systems where we will have to connect to import automatically data. People from environment. Actually, all the aspects will require at least one representative to have his insights, knowledge, and will be required for the validation also of the results. And okay, last question maybe. Thank you again for all those questions. Does it use neural networks? So this tool is using artificial intelligence methods, which are mathematical programming. So we are using solvers that have this intelligence to search for the best solution within the feasible domain set by the restrictions. So these are those techniques of advanced analytics that we are using, there is no real neural network or machine learning, because at this level, we already have, through the regressions, already enough knowledge to create relation and equations between the variables that are on our interest at that level, meaning strategic and tactical level, which makes that it's not required to ask for an artificial or machine learning to create those relations for us. So we do that work with the data. We are using the data to calibrate and to find new relations between the variable, but not with neural network. It's really unnecessary. And every time I answer a question, there is another question coming. So this question is about, does the tool work with SAP? So yes, we have many input data that most probably are already in SAP. So what we will then do is create a direct importation of those data that will be used in the model. So the two tools will not actually be connected. They're just a communication channel where, and usually this is done by web service, then we are not restricted to any technology and any language to communicate with external systems. So through a web service, we can then, from the system, request a certain query to SAP that will process and make averages of the data for instance, the cost, the chemical composition, the order book, and then send back to Quandec. That would be the responsibility of Quandec, all the data that has been requested, and then Quandec will process this data and pass that to our optimization engine. Okay, well, I think I answered all the questions. I'm sorry if I missed some. If this is the case, please enter in contact right after and ask your question directly to me. You have all the contacts to do so. Again, thank you very much for your participation. We will stop now this seminar, but please enter in contact. As I said in the beginning, this video will still be available. So please share this video with your colleagues or any people who might be interested in that subject and working for a steel plant. I'm sure they will have interest in that subject. Thank you very much again. I'm Emmanuel Marchal from Cassotis. See you next time.